welcome all to the next session of Fundamentals of Food Process Engineering Problem Solving session. So in this session we will discuss the syllabus related to week 9. So we'll move on to the first question. Match the following. List 1. A. Cyclone separators. B. Centrifugal filters. C. Drag coefficient. D. Cake filters. And list 2. First is centrifugal force, 2 pressure difference, 3 centrifugal force plus gravitational force, and 4 shape factor. So your options are A1. Your options are these. So we'll discuss each and every kind of these separators one by one. So the first is a cyclone separator. So what a cyclone separator is that it's mainly used for solid gas separations. That is, if you want to separate any solids from a gaseous material, we use cyclone separators where we'll feed in the, let's say we are going to, it's mainly used for cleaning air. That is, it will separate out the dusty particles from the air. So you feed in dirty air through a tube, and you have a cylindrical equipment with a conical end. And what happens is when the dirty air enters the cylinder, it kind of makes a rotatory motion, and because of this rotating motion, circular motion, a vortex is formed, or basically a cyclone is formed. So this mini cyclone, what happens is when this mini cyclone undergoes, there is both centrifugal force, and on top of that, this vortex kind of comes down along the equipment. So what happens is when the dirty air forms a cyclone, it comes down the equipment at one point of time. Because of this centrifugal force, the dust particles, that is the solid particles, will hit the walls of the equipment and come down due to gravity. So what happens in cyclone separators is that the dust particles will undergo an effect of centrifugal force as well, and when it hits the walls, it comes down because of gravitational force. So in case of cyclone separators, you will have both centrifugal force and gravity force acting as a mechanism for separation, and this is mainly used to clean your gaseous materials. And centrifugal filters are very straightforward. Basically, you will have a kind of a vessel with membrane on the sides of it. So any slurry or anything that you put inside the vessel, and you put it inside a centrifuge and spin it at a certain RPM, and when that is taking place, because of the centrifugal force, all the liquid will be forced against the walls which contains the membrane. So since the liquid is now forced against the walls that contains the membrane, all those particles that are smaller than the filter pore size will come out, whereas the larger particles will remain here. So this is both centrifugation but in the presence of a filter, and hence is known as centrifugal filters. So in case of centrifugal filters, it's a centrifugal force that is helping in the separation process. So for A, it is 3 centrifugal force plus gravity, and for B, it is 1, that is centrifugal force. So drag coefficient is actually a dimensionless number, where it is highly dependent upon the shape of the particle and the orientation of that particle with respect to motion. So you have this drag coming in when you have a particle that is flowing in a fluid. So let's say you have a spherical particle that is kind of settling down in a sedimentation tank. So at that point of time, the particle will undergo something known as a drag force opposite to its motion. So if the particle is coming down, your drag force will be in the opposite direction, that is going up. So in this drag force, you will have something called as drag coefficient, which is highly dependent upon the shape of the particle. So for a spherical particle, you will have a different drag coefficient. For any other shape of the particle also, you will have a different drag coefficient. So this is based on the geometry of the particle and the way in which it is oriented along its motion through the liquid. So for drag coefficient, it is the shape factor that comes into play. And for cake filters, you can see cake filter is the normal filtration process that you see. You will have a filter membrane, and you pass the slurry through the filter. So what happens is over time, all your particles that are bigger than that of the filter size will accumulate on the top, whereas those that are smaller will come down as filtrate. So this accumulation of the bigger particles actually forms a cake, which is why it is known as cake filters. So driving force for cake filters is the pressure difference across the filter medium and the cake. So initially you will not have the cake. So initially you will just have the filtration process. But as the filtration process proceeds, you will have more and more accumulation of the larger particles on the filter and hence forming a cake. So over time, you will have resistance from the filter medium and resistance from the cake. So you need to apply certain pressure across the filter medium as well as the cake to ensure that the liquid is flowing through the filter medium and getting filtered. So the driving force for the cake filters is the pressure difference across the filter medium through which you are filtering the material and the cake, that is the deposition on the filter medium. So the answer to this question is option B. Moving on to question 2. The centrifugal force acting radially in a cyclone can be written as WV square by GR, WV square by R, GV square by WR and WV by GR, where V is the velocity of a particle, W is the weight of the particle and R is the radius of the separator, or the radius from which the particle is on the axis of the cyclone. So a centrifugal force for anything, not just a cyclone, for even for a centrifugation process or so, the centrifugal force can be given as m omega square r, where m stands for mass of the particle, omega stands for the angular velocity, which is given in radians per second. So yeah, we are discussing the centrifugal force acting radially in a cyclone. So the options are omega v square by w v square by gr, w v square by r, g v square by wr and w v by gr. So this, we are asking the centrifugal force acting radially in a cyclone separator. So where w stands for weight of the particle, v stands for velocity, g stands for acceleration due to gravity and r stands for radius of the separator. So we were discussing that the centrifugal force for any particle can be given as m omega square r, where m stands for mass of the particle, omega stands for the angular velocity and r stands for the radius of the particle. So this omega is actually given in radians per second, and angular velocity can be written in terms of the tangential linear velocity as v by r. So v is the tangential velocity and r is the radius of the radius from the center. And again, since all these options are given in terms of weight and not in terms of mass, weight is equal to m into g. So when you substitute your omega and weight into this equation, your m will be equal to w by g and omega will be omega square will become v square by r square. So r square and r will get cancelled, and what you will have is Fc is equal to W v square by g into r. So this is the equation for a centrifugal force in a cyclone separator. So the answer to this question is option E. So moving on to the next question. In a cyclone separator, the lighter particles take dash to settle. A shorter time, B longer time, C very short time and D equal time. So any clue what could be the answer? You could either unmute yourself or you can post it in the message chat. So as we discussed in the first slide, in a cyclone separator, what happens is you will pass in air with a lot of particles in it, and you need to separate these particles from the air to get cleaner air. So we send in air with a lot of particles, and what happens is that when it enters into the cyclone separator, it forms a kind of a rotatory motion, thus experiencing centrifugal force. And because of this rotatory motion, it will often hit the walls of the cyclone separator, and once the particle hits the walls of the cyclone separator, it falls down due to gravity, and then whatever remaining air is there will now rise up in the cyclone separator again in the form of a vortex only, and then here you will get your fine clean air with only fine particles, and here you will get your coarse particles that fall due to gravity. So when you see here, any particle at a time will experience both centrifugal force drag force as well as gravitational force. So what happens is that when you have very lighter particles, it takes a longer time to settle. Sorry, just a minute. So it takes a longer time to settle because the moment you have something called as a drag force, you can apply the Stokes law to find out the settling velocity of the terminal velocity or the settling velocity of a particle. So the settling time of a particle in a cyclone separator, once you equate the centrifugal force and the drag force, this is the equation that we get. The derivation for this equation is given in the last lecture. So VTR stands for the settling time of the particle equals to G rho P minus rho dP square by 18 nu into V square tangential divided by GR. So G stands for your acceleration due to gravity. Rho P stands for your density of the particle. Rho stands for the density of the fluid in which the particle is suspended. dP stands for the diameter of the particle. Mu stands for viscosity of the fluid that is in which the particle is suspended. V square tan is actually the tangential velocity of the particle because it's moving in a rotatory motion. We are dealing with the tangential velocity here, and G is acceleration due to gravity, and R is the radius of the particle. So this is how you get the settling time velocity, settling velocity of a particle when you apply your drag force. So the settling time is actually settling time is inversely proportional to the square of the diameter. So what happens is that since your smaller particles have a smaller diameter, your velocity will also be less. Now since the settling velocity is less, it takes more time for the particle to now settle. So since your velocity is directly proportional to dP square, dP is less for smaller or lighter particles. And hence velocity also decreases. Since velocity decreases, the time taken for it to reach the bottom of the cyclone separator also increases. So hence finer particles take longer time to settle. So what happens is, if it does not get enough time to settle and the air already starts going upward in motion, what happens is these fine particles will not be able to separate. You will only be able to separate the coarse particles which settle down quicker. Those particles that take a long time to settle will not be acted upon by the gravitational force. In fact, it will go along with the supposedly clean air. So you need to accordingly manipulate the amount of time a particle spends inside the cyclone separator to get as pure air as possible in the outlet. So the answer to this question is option B. Lighter particles take a longer time because they have a smaller diameter. So any doubts? Okay, so moving on to question 4. Statement 1. The destoner separates the grain mass into two fractions based on the surface texture. And statement 2. The spiral separator separates the grains as per the specific gravity. So which of these statements are true or false? Any clue? So destoner, any idea how a destoner works, the working principle of a destoner? The name itself suggests what it does, but any idea how it brings about this separation? Okay, so what happens in a destoner is that it's mainly used for grains that have a lot of stones, like say rice or so. It's often used for separating grains only. So what happens is you feed a grain product with stones or with contaminants into the destoner, and what happens is you here, as you can see here, there is air being supplied onto a tray onto which the feed is fed. So your feed with the stones as well as the grains will be fed onto a tray that has holes. So with these, because of these holes, the air that is passed on to the tray will kind of make it as a fluidized compartment in this particular region. So the air will try to lift off the lighter grains, whereas the stones that are much more heavier because of higher specific gravity will not move. So the grains will become much more fluidized kind of a nature, whereas your stones will remain stationary. So because of this difference, what happens is the tray is now being vibrated at a certain angle and at a certain velocity. So because of this vibration and a certain angle, what happens is this difference in specific gravity results in stones going in one direction and a clean product going in other direction. So you need to accordingly adjust the angle, the tilt of the tray, the velocity of the air that you pass through to make the grains rise, as well as your vibration, the number of vibrations that you give. So all these will play a role in separating the stones and the clean product. So the destoner separates the grain mass into two fractions based on the surface specific gravity, that is the weight of the particles, rather than the surface texture. So the statement 1 is false. So what happens in a spiral separator is that, so your statement 2 is spiral separator separates the grains as per the specific gravity. So what happens in a spiral separator is that spiral separators look like this. So you'll have multiple spirals going down and you'll actually feed your grains along with your contaminants on the top. So as you can see here, there are two kinds of spirals here. There you can see an inner spiral here and an outer spiral here. So the inner spirals are called the inner region is called inner spiral flight, and the outer region is called an outer spiral flight. So what happens is that you put the feed on top, and due to gravity, all of these will all the particles will start spiraling down. But what happens is that only the round materials roll faster and gain a higher momentum, whereas the flat materials kind of slide instead of rolling. They have a different kind of a motion instead of rolling, whereas your round particles are more capable of rolling down faster. So because they roll down faster, they gain a higher momentum, and as they go down, the orbit increases. That is, initially they'll all of them will pass through the inner spiral flight, but as the round particles gain momentum, it will become the orbit will start increasing, and what will happen is from the inner spiral flight they are thrown out into the outer spiral flight. So your round particles that gain higher momentum are thrown into the outer spiral flight, whereas your non-round materials or flat materials kind of slide along the inner spiral flight only. So at the bottom of the spiral separators, you will collect the inner spiral flight material separately and the outer spiral material flight separately. So here you can see that it is the roundness of the materials that affect the separation rather than the specific gravity. So you have two separate outlet valves that collect the round particles and the non-round particles. This is often used for separating good grains, good seeds or peppers or all those sorts. So statement 2 is false. It is the roundness of the material that dictates separation and not the specific gravity. So the answer to this question is option D, that is both the statements are false. So any doubts so far? If you want me to repeat any part of the answers, I can repeat that as well. So you can just put it in the group chat if you want me to repeat any part of the answer. Okay. Moving on to the next question. Statement 1. Clarifying filters are used when particle size that the particles that needs to be removed have a size smaller than that of the filter pores. And statement 2. The cross flow filtration involves the slurry passed perpendicular to the filter medium. So which of these statements are true or false? So what are clarifying filters here, and how is it different from a cake filter that we discussed? So clarifying filters look like this. So you have a large filter medium with kind of pores inside it, and it happens that this pore size is larger than the size of the particle that needs to be removed. So your particle size that needs to be removed will be smaller and your pore size will be larger. So in that case, your particles will actually go through the pores, but as it passes through the filter medium, it gets stuck in between the filter. So that is how it is getting clarified. Instead of being accumulated on the top itself, it passes through the filter and gets accumulated in the inside the pores of the inside the passage of the filter medium. So the clarifying filters are different from sieves, that all the sieving or the screens that you see for separation, screens will have a smaller pore than your particle size. So it will accumulate all the particles that are bigger at the top itself. So the screens will have a pore smaller, whereas in case of clarifying filters, the pores will be larger. So their separation will be based on your accumulation of the particles inside the filter medium rather than outside the filter medium. So statement 1 is true. Clarifying filters are used when your particle size to be removed are smaller than that of the filter pores. And in fact, clarifying filters are used for slurries that have small number of solids. If you have a large number of solids, you will just end up choking the filter medium. So this is used for fluids that have small number of solid particles. So statement 2, cross-flow filtration involves slurry passed perpendicular to the filter medium. So what happens in a cross-flow filtration is that you have your slurry that is passed in a direction that is tangential to the filter membrane. So you are not passing the slurry perpendicular to the filter medium, you are passing it in a tangential way. So what happens is when you pass a filter medium but very high velocities in a tangential way, you are preventing this deposition that might happen. So if you pass the slurry in a perpendicular way, as the time increases, you will have your larger particles being deposited as a cake. But when you pass the slurry in a tangential manner, because of the high velocity, whatever minimal cake that is being deposited will be removed because of that very high velocity in a tangential manner. So cross-flow filtrations are often used when you don't want a cake deposition on your membrane. So, statement 2 is false. So the answer to this question is option C. The first statement is true, that is your particle size, your pore size is larger, and your statement 2 is false, that is cross-flow filtration involves slurry passing tangential to the filter medium. So any doubts in these concepts? Okay. So moving on to question 6. We'll start with numericals. For a cyclone 0.3 meter in diameter with a tangential velocity of 15 meter per second, calculate the separation factor for the cyclone separator. So as we remember, the cyclone separator will take in the air with the particles, form a cyclone, come down, hit the walls of the cyclone separator, and then the larger particles will come down due to gravity, whereas the rest of the fine air will again rise up in a vortex kind of manner, and you can collect the clean air from the other end. So for this, what we need to calculate the separation factor. So any clue what a separation factor is in a cyclone separator? Okay, so since there are, as we discussed in the first slide, there are two forces that act in a cyclone separator. The first one is the centrifugal force that causes this spiral-like movement or a cyclone movement, and second is the gravitational force that helps when the particles hit the wall and comes down and gets collected. That is where the gravitational force also comes into play. So you have two forces acting here. So the separation factor is actually defined as the ratio of the centrifugal force to the gravitational force. So this ratio will determine how great is your separation factor of that cyclone separator. So separation factor is equal to your centrifugal force divided by your gravitational force. So as we discussed, centrifugal force is equal to mv square by r, where v is the tangential velocity, r is the radius of the particle, and gravitational force, as we know, is equal to mg. So mm gets cancelled. So your separation factor is equal to V square by Rg. So for this, what is the, for the given numericals that we have, where your diameter is 0.3 meters and tangential velocity is 15 meter per second, what is the separation factor that we get? So S is equal to 15 square divided by 0.15, because we need to deal with the radius and not the diameter. 0.15 into 9.81. So when you calculate this, you have an S of 153. So your answer to this question is option A. So what happens when you use a larger cyclone separator is that, for the same velocity, if you use a larger cyclone separator, your R will be higher now. So since your R is higher and your V remains the same, your S will go down. So for larger cyclone separators, your separation factor actually comes down. The efficiency also comes down. And you can always argue that you can increase the velocity of your air that you send in, but there is always a limitation to how much you can increase the velocity. So larger larger cyclone separators are not much preferred because your S value goes down and hence your efficiency also goes down. So instead what people have is they have multiple small cyclone separators, and this helps in cleaning a larger amount of air rather than using one large cyclone separator with a poor separation factor. So for a smaller cyclone separator, your S values can even go up to 2500. So the larger the S value, the better the separation, better the efficiency of the separation process. So the answer to this question is option A. Any doubt of what a separation factor is and how it can be related to your efficiency of separation? Okay, moving on to the next question. The cut diameter in a screen process and a cyclone separator is given as A. The diameter at which 90% of the particles can be removed. B. Diameter at which particles cannot be separated. C. The diameter at which the particle size is the same as the width of the screen opening, and the diameter at which 50% of the particles are removed. So this one, diameter at which the particle size same as the width of the screen opening, is for a screen process. Whereas for a cyclone separator, you are assuming that 50% of the particles are removed. Or D, the minimum diameter at which separation is possible. So any idea what a cut diameter is? Okay, so what happens in a screen process? Screen process is very straightforward. So you have a screen with a mesh-like structure, or you have those mesh have kind of openings, and when you put your feed onto the mesh, you kind of vibrate the mesh so that particles smaller than that of the opening comes down, and particles that have a larger than the opening size remain on top of the mesh itself. So that is what happens in a screen process. And cyclone separator is what we've been discussing throughout this presentation. So for a screening process, a cut point diameter is the diameter in which your particle size is same as that of the width of the screen opening. So if your pore size or your screen pore size is the same as that of your particle size, that particular size is known as the cut point diameter for a screening process. Whereas in case of a cyclone separator, your cut diameter or your cutoff diameter is the diameter at which 50% of the particles can be removed. That is, the particles can be removed with 50% efficiency. So for cut point diameter for screen process and cyclone separators are different. So the answer to this question is option C. For a screen process, it is the same diameter as that of the screen opening. And for a cyclone separator, you are not dealing with the screen in the first place. It is more of a separation based on centrifugal and gravitational force. So for a cyclone separator, the cutoff diameter is the diameter of the particle where 50% efficiency can be observed. So the cyclone separator, the cutoff diameter depends upon the geometry of the cyclone separator that you have, the velocity in which you are feeding in the air and all those. So the answer to this question is option C. Any doubts on what a cutoff diameter is? Moving on to question 8. A basket centrifuge of 0.6 meter in diameter and 0.4 meter high contains 50 kg of water. Calculate the pressure at the wall of the centrifuge if it rotates at 6000 rpm. So, what law do we use? So what equations or what concept do we use to solve this problem? How do you find out the pressure at the wall of the centrifuge? So the force that mainly acts on the centrifuge is the centrifugal force. So what is the formula for the centrifugal force? So the formula for the centrifugal force, as we discussed in the second slide, is Fc is equal to m omega square r. So m is the mass of the liquid or the product that you are trying to centrifuge. Omega is the angular velocity given in radians per second, and r is the radius at which the particle or the liquid that you are separating is present from the central axis. So let us say this is the centrifuge that you are dealing with, and your dotted areas are the are where your liquid is present. In this case, it is the water. So these dotted areas is where your water is present. So since your centrifuge is rotating, all your liquid will tend to move towards the walls because of the centrifugal force. So this area will not be this area will just be your air, or your will not contain any of your liquid, whereas towards the walls you will start seeing your liquid. So the inner layer of the liquid or the water can be given as Ri, and let's say the entire bowl of the centrifuge can be given as radius r. So you have Ri, which is the inner layer of the liquid, and capital R, which is your full radius of your centrifuge bowl. So let us say we take a small strip of liquid at some distance r and with a thickness dr. So what we do is we differentiate for that particular strip, the small centrifugal force, that is dFc, that it experiences is equal to dm omega square r. So m, when we want to express it in terms of density and volume, can be given as dm is equal to rho a into dr. So rho is your density, a into dr is your volume. So rho into V is equal to m. That is what we are applying here. So for a small strip, that is the small mass of liquid that it contains, that is equal to rho into A into dr. So A into dr will be the volume of that small strip, and rho will be the density of the liquid. So when you substitute this back in this equation, you have your dm will be rho A dr. Now we want to find the pressure at the walls. So pressure is equal to force by area. So pressure at this particular strip is equal to dFc by area, that is force by area, that is pressure, is equal to, when you substitute m dm here and area gets cancelled, so rho omega square r dr is what you get. So rho a dr into omega square r, and now when you integrate this from 0 to p, that is or from p1 to p2, that is the pressure gradient across the centrifuge, p is equal to rho by 2 omega square, and since r dr, when you integrate, you will get r square by 2, and the liquid, since it is present only from ri to r, you will consider ri as your lower boundary and capital R as your upper boundary. So r square by 2, when you integrate from ri to r, you will get r square minus ri square. So this is the formula that you apply for calculating the pressure at the wall of a centrifuge. So where r is the radius of the bowl, Ri is the inner layer of the liquid obtained from centrifugation. So from in this equation, we already have the rho. Since we already know the density of water, we have rho. we have omega, we have the angular velocity in which the centrifuge is rotating. We only need the capital R and the small RI, that is the inner radius and the outer radius of the liquid. So in order to calculate that, we know that the liquid is present only between Ri and R in the cylindrical tank. So we can calculate that from the density and mass of the liquid that is given in the question. So mass is given as 50 kg and we know that density is equal to 1000 kg per meter cube. So total volume of the liquid that is present inside the centrifuge is equal to mass by density. So this volume, since it's actually when it spins, it's like an annular cylinder. So for an annular cylinder, you can get the volume as pi r square minus ri square into h. So since the liquid is present only between ri and r, so this is the annulus of the liquid, r square minus ri square, and this equation will give you the volume of the liquid present inside the centrifuge. So we already have the mass, we know the density, and we know the height of the cylindrical tank, which is given as 0.4 meters. So we'll substitute these values in this to calculate r square minus ri square. So mass is equal to 50 kg, rho is equal to 1000 kg per meter cube. You have pi r square minus ri square into h, which is 0.4. So from this we can calculate r square minus ri square equal to 0.0398 meter square. So any doubt in how this came out, the volume of the liquid, or how we derive the pressure equation? If you guys have any doubts, I can explain it again as well. Okay, so I'm assuming you guys understood. So moving on. So the pressure as we derived, pressure is equal to rho omega square by 2 r square minus ra square. Now you have rho, you have omega, you have r square minus ra square derived from the density volume relationship. So pressure is equal to rho by 2, that is 1000 divided by 2 into, now omega square is given as rpm, but as I in the question the rotation speed is given in terms of rpm, but as I mentioned, omega is always expressed in radians per second. So in order to convert rpm to radians per second, you multiply it by 2 into pi. So since one radian is equal 1 rpm will be given by 1 radians, so 2 into pi into omega square, that is 6000 rpm divided by 60, because we need per second and not per minute. So to convert everything into SI units, we convert your rpm into radians per second. So for converting rpm into radians per second, we multiply it into 2 into pi. So 2 into pi into the rpm that is given per 60 for to convert minutes to seconds. So 6000 divided by 60 the whole square into r square minus ra square that we calculated previously, that is 0.0398. Is this clear how omega is 2 pi n? So the moment you have anything in rpm, that is actually n. So always you need to convert that n into omega, that is the angular velocity, and then only substitute in all of the equations. So from this we calculate the pressure to be 7850 kilopascals. So accordingly, since the pressure is very high, for such large amounts of 50 kgs of water you are dealing with, your centrifuge material should also be made of such a sturdy material to withstand such a high pressure. So any doubt how in any of the equations, the derivations or the concept that we used? Okay, so moving on to the next question. The answer to this question is option B. So moving on to the next question. A separation process requires centrifugation of a product at 10,000 G. A centrifuge with an effective bowl diameter of 24 centimeter is available. So now what should be the speed of the centrifugation to meet this specification, that is that the product requires 10,000 G. What should be the speed of the centrifugation in RPM? So, any idea how to convert your G force into RPM? Okay, so when you have a centrifugation speed given in terms of G, it is known as the G force, or you can mention it as RCF. So this RCF, we need to convert it into RPM as given in the options. So how you will do that is that this G can be considered, this 10,000 into G can be considered as a centrifugal acceleration or the G force. So centrifugal acceleration is equal to 10,000 into G, and the diameter of the centrifuge that is available to you is 24 centimeters. So the centrifugal acceleration or your G force can be given as omega square into R. So 10,000 into G, which is 9.81, is equal to 2 pi n square into R, which is available to us, which is 0.12 meters. So here you will find out what is N and then convert it into RPM. So when you substitute all the values, we have 10,000 into G into 2 pi N is what we need to find out, and R we have is 0.12. What is the value of N that you are getting? So N is equal to 143.9 143.9 radians per second. So when you convert it into minutes, you will divide it, you will multiply it into 60. So N is equal to 143.9 RPS into 60, which is 8634 RPM, which is revolutions per minute. So the answer to this question is option D. So any doubt? So whenever you have a G force, you can consider it as the centrifugal acceleration, and from that centrifugal acceleration you can convert your RCF or your G force into RPM. So for it's the same centrifugal acceleration, your different sizes of your centrifuge will have different RPMs. So any doubts? So moving on to question 10. A sedimentation tank 1.6 meter wide is fed with a slurry containing starch particles of 30 micrometer diameter and a density of 1220 kg per meter cube in water. That is, the starch particles are suspended in water, and 30 micrometer is the diameter of the starch particle, and 1220 kg per meter cube is the density of the starch particle. So what is the length of the settling tank required to treat 4,300 liters of the slurry per hour? So what are the forces that occur in a sedimentation tank? We have particles suspended in a slurry. What forces do these particles experience? So when you are dealing with sedimentation, so you have three forces that is acting on the particle. First thing is the weight of the particle, that is the gravitational force. The second is the buoyancy force that occurs when you suspend a particle inside a liquid, and then you have your drag force. Since your particle is now flowing in a fluid, the particle will also experience a drag force because of the fluid. So you have three forces acting. In downward direction, you have the weight of the particle or the gravitational force, and in the upward direction, you have the buoyancy force as well as the drag force. So the derivation for this particular settling velocity or the settling time that we even discussed in the cyclone separator, the derivation for this is given in the one of the lecture videos, as well as in, I think, chapter in your week 2 sessions as well. So the settling velocity of a particle in a sedimentation tank can be given by applying Stokes law, and that you can calculate by V is equal to rho P minus rho F G dP square by 18 nu. So rho P is the density of the particle, rho F is the density of the fluid in which the particle is suspended, G is the acceleration due to gravity, dP is the diameter of the particle, mu viscosity is the viscosity of the fluid. So with these values you can calculate the settling velocity, and always velocity can be given as Q by A, where Q is the volumetric flow rate by A is the area. So we already have rho P, which is 1220 kg per meter cube, and since the starch particles are suspended in water, your rho F will be that of water. So rho F is 1000 kg per meter cube, dP is given as 30 micrometer, and mu for a viscosity of the water is 0.001 Pascal second. So when you substitute all these values, 4300 liter, we are converting it into meter cube. So 4300 into 10 power minus 3 meter cube, which is 4.3. And since it is liter per hour, we are converting hour into seconds. So 4.3 divided by 3600 will be your cube. And area we still don't know yet. And rho P is given as 1220 kg per meter cube. Rho F is that of water, that is 1000 kg per meter cube. G is acceleration due to gravity, 9.81 meter per second square. dP is your diameter of the particle in meter. So 30 into 10 power minus 6 the whole square. 18, and viscosity of water is 0.001 Pascal second. So when you compute the area that is required for the settling tank, area comes out to be 11.08 meters square. So you have a large tank and you feed the slurry and you wait, you keep a certain residence time. So what happens is that over time your particles will start settling down onto the bottom of the tank. So this bottom of the tank has the area of 11.08 meters square. So we already know the width of the tank, which is 1.6 meters. So area is length into width. So length we don't know, that is what we need to calculate, and width is given as 1.6 meters. So L into 1.6 is equal to 11.08. From here you can calculate the length of the settling tank required, that is 6.95 meters. So the answer to this question is option D. So any doubts how to calculate the settling velocity of a particle in a sedimentation tank? And from that settling velocity we calculate the area with the volumetric flow rate given. And from area we can calculate what is the dimension of the sedimentation tank required to enable 4300 liter of slurry to be treated. So any doubts so far?